Good afternoon. Welcome to this joint colloquium. Today we have Professor Paul Ho standing over there. You must have seen him a month ago on all this TV. If you don't see it, our president already know their work and even write something. And so it's a very important thing. So you will see how. If you believe it, you see it. Right? Well, Paul was our joint professor. So very glad when we invited him, he come back to give this talk. And today I asked him, thank you very much. He said, well, it's my duty. Yes, I think he has the sense of the duty to our department, to Taiwan, and to the big science in astrophysics. Paul graduated from MIT and then moved to Berkeley with a postdoc, then went to Harvard as a researcher, project scientist, project scientist, and then moved to Harvard Smithsonian before he returned back to Taiwan 17 years ago as the director of the ASIAA. That time was still in preparation and to become an institute. Under his leadership, now it's a full-grown institute. Now he has stepped down as a director for that. He has a new directorship as the East Asian Observatory. So all this Japan, Korea, Taiwan, and China together to do science in astrophysics. So let us now welcome Professor Paul Ho to tell us what a black hole looks like.
Thank you, Sharon. It's good to be here. If we could lower the lights. It's good to give the talk at Taida Physics because I haven't given this talk yet at IAA. So people in IAA ask me, what do I do all the time? And, so here's the first image of a black hole. But since it's very black, I need to turn the lights out. But maybe it's not so easy.
Not so easy.
It's
not so easy to see the black hole.
Yes. Okay, here we are. That's a black hole. So what is the conclusion? People say, when you see this image, what's the first impression that you have? Was it exciting? Was it what you expected? And my answer is, yes, it looks black. And second, it looks like a hole. That's why it's a black hole. So of course, to see this image took a lot of work. And Taiwan played a very strong role in making this image. It's, to me, a seminal moment in astronomy when we are able to see this. Now, how do I advance this?
Too black.
It doesn't move. Why? Okay. So I have to stand here. So it got a lot of press on April 10th, as you know. It's on the cover of all the major newspaper. But you know that you really have made the problem important one when it shows up on Google page, right? So, somebody made this. I saw how this artist had done it while he was in a car. He drew this, and in a few hours got it onto the Google page. And you can see that they captured the idea that the black hole sucks everything in. And the black hole even have a Hawaiian name, Hawaii. We had a Hawaiian linguist named the source, and its meaning comes in this a 1,000-line chant in the Hawaiian culture, historical chant, in which there's this word Poehi, which means the embellished, fathomless, dark creation. So it's kind of a nice feeling in Hawaiian on what this dark black hole is. And notice here it is the governor of Hawaii declaring the Povei Day for April 10th. Congressman Case from Hawaii read into the record the accomplishment of this experiment. He is very important because he sits on the appropriation committee. And then, of course, this one is our President Tsai Ing-wen also had an Instagram commenting on that. This is a nice result. So it caught the attention of quite a lot of people. Now, black hole research actually has made a lot of progress. So I'm going to actually mention a few of these, okay? The first one, of course, is a few years ago, we had the detection of the gravitational waves, right? And then the progenitors of gravitational waves is something that we're working on. And then people have been working on the orbital motions near the galactic center black hole, in particular detecting the motions near the event horizon. And of course, this particular experiment is the imaging of the event horizon itself and to study the general relativity effects. The common theme here is that all of these techniques require interferometry. So for astronomers, beginning students, this is the message again. Interferometry is an extremely important technique. Why is that? Because it allows us to achieve very, very high angular resolution. And in physics, when people ask me, how do you get a Nobel Prize? I say, I don't know how you get to a Nobel Prize, but the most important thing you do in physics is to measure something extremely precisely. And that is the goal of these physics experiments, to measure things extremely precisely. And of course, Einstein predicted the black hole in 1916. General relativity is quite elegant and simple. It's driven by the idea that speed of light is constant and finite. And all of the tests that we have done so far has upheld the theory as he predicted, okay? Of course, the main crux of his idea is that mass will warp the space-time so that the space-time itself is distorted by the presence of mass, okay? And of course, depending on how much mass there is, how much the distortion takes place. And this is a very important concept because reaction to gravity is not just mass itself. Light must also conform to this distorted space, and therefore light itself has to follow the gravitational effects. So LIGO, of course, heard the signature from gravitational wave. This experiment, an interferometer, was designed to be very carefully listening for the gravitational wave, which is emitted in these interesting events, such as a collision of two black holes, for example, or massive neutron stars, right? And you know that the gravitational wave detectors are now in 4 sites. LIGO itself has 2 sites. Virgo is in Italy, and then Kagura is coming up in Japan. And I just heard that India has also now joined LIGO, and they will establish yet another point, okay? So the signature of gravitational waves is seen as a function of frequency and time, right? So it's a ripple that you can see has a frequency signature, but in particular, it has this rippling pattern, okay? This ringing pattern with time is very important. And here is one of those cases where theory is absolutely important, because without the theory, you just see some ripples. Never mind that you can say that it's an event, but you just don't know what it is, right? But the theory predicts what that ripple comes out to be. And that's actually what makes people believe that you have detected gravitational waves, is because of the theoretical prediction. And now, of course, many sources have been seen. Somebody told me, it's today at lunch that, maybe it's coming now once a month, once a week, more and more of these with the classic signature that as a function of frequency, you can see the dispersion with time, and then this classic rippling, okay? What do you do with these gravitational wave detections, okay? So the reason why I go through these 2 first things is to tell you that Taiwan actually does play a role in this kind of experiments, okay? So once you've detected them, because you have 2 of them in the case of LIGO, the detection slightly later at Hanford following Livingston by something like a few milliseconds. This allows us to position the possible likely targeting of the source on the sky, okay? When you have 2, that error circle is quite large in the sky, okay? And when you have add the other interferometers, you will be able to triangulate the position much better, okay? But for this event in 2017, this particular project actually had some very important contribution. This is the Hyper-Suprime Chem project that Taiwan is involved in on the Subaru telescope. This is a very large camera at the prime focus of this 8-meter telescope. and it's allowed. It was put into operation in 2012, and in 2017 it began to actually take data, and that it's now undergoing this large survey. But it has a very large field of view. For example, it takes in the entire Andromeda galaxy in its field of view when it does this. So with this experiment, what it can do with the hyperspectrum camera is that it's actually a spectroscopic instrument also, because there are a series of filter banks, filters at different wavelengths that you can slip in front of the camera that you can measure the redshift. Therefore, on the sky, you can map a very large swath of area, but also in redshift space, be able to position it. Okay, this redshift measurement is actually quite important in this case, because what they have found is that in mapping this very large area, they can cover it fairly quickly, and as a result, survey and found an event which they saw with the HSC instrument on Subaru, an apparent neutron star merger event where it faded with time, okay, over the order of a few days. This event, 1708-17. So here it is. What you can see is the time profile. Okay, so the key here is that they measure the light curve as a function of time in days here, and then measure it for different optical and infrared, okay, near infrared. And they see this profile which they model from this kilonova model of the colliding neutron stars, and they establish that this is likely to be the source of the event which driven the gravitational wave. So in this type of research, the future is actually working on these very large format cameras on optical instruments. Taiwan is already working on this HSC. They're also working on PFS, but we are now also working on likely the next generation of large telescope. We're in discussion with the extremely large telescope, which is the first instrument which will come online, very large optical telescope that will be built in the next 10 years. So of course, directly you can join in, and some people have joined in on this gravitational wave research, but even in the follow-up experiments, Taiwan also has a role to play. The other thing, of course, is that you can feel the gravity. By that, I mean you actually feel the gravitational forces. In this case, a stellar field around the Sagittarius star galactic center. You can see the orbit of this source, S2, a star that is in orbit. You can see many stars are in orbit around the galactic center, which is quite an amazing thing that you can see it, okay? But this particular one is really amazing in that in a few years, it has a very, very tight orbit around the galactic center, which is across here, okay? So this has been done with this gravity instrument as well as Keck telescopes in California. And this particular experiment I tell you about is the so-called very large telescope interferometer. Astronomers are not very good at naming things. We tend to call them the large telescope, the very large telescope. So this is the very large telescope interferometer in Europe. And it's 4 8-meter telescope combined together in interferometer. It even has little outliers that are very small instruments that are also hooked in together to do this interferometry experiment. And it's a very elegant experiment in that in the field of view, it actually does a number of things. This particular instrument called gravity, it takes a look at a guide star from which it uses adaptive optics to remove the atmospheric seeing. And then in the field of view of the interferometer, it actually has a fringe tracking star, which actually check the phase for the interferometer baselines, okay? So as a result, this interferometer operating in the optical with 6 baselines achieve a resolution of 3 milliarc seconds, okay? 3 milliarc seconds is quite good, and it has a relative accuracy of 40 microarc second for astrometry. Not imaging, relative positioning, good to 40 microarc second. This is quite an enormous achievement for this group. And you can see that, it's almost like a benchtop laboratory experiment. If you go visit them, you can see that in the bowels of this interferometer, in the telescope, there's huge delay lines, optical delay lines, running back and forth between the telescopes. And then there's a huge number of mirrors, gathering the light and redirecting them and then combining them and all the way at the end to the detector. Okay, you can ask how much light actually get to the end, starting from the beginning. Okay, the answer is just a few %. So this very large telescope gather all the light that it can gather just a few percent gets to the detector and it's able to calculate what it's actually seeing. So what do they see? Okay, so astrometry-wise, that is tracking the star, you can follow this orbit extremely nicely, and it gets very close at the closest approach to the galactic center black hole. You can see the size scale here. This is 400 AU. Okay, this one is actually looking at spectroscopy. It's looking at, I think, the Lima gamma line, and actually tracked the gas around this pocket to see the motion, relative motion in the sky. And you can see that the motion turns out to be on the order of thousands of kilometers. Okay, very accurately tracking this orbit. Okay, very accurately tracking this orbit. And what it finds is that you can see the motion of this object, S2, which is not clear what it is a star, I think, and it is tracking it very accurately. Day to day, you can see as it goes through the closest approach, it's moving very quickly in this orbit at about 8,000 kilometers per second, okay? And the positioning is very accurate in the sense that you can also see the gravitational pull on the gas. And this is a measurement of the gas relative to the Kepler profile in the previous orbit, okay? If you take this orbit and just calculate the Kepler orbital motion in this motion, and you subtract it, you find this residual right in 2019, that period. And that, of course, is due to its closest approach to the galactic center black hole. And that's the GR effect, actually pulling on it. And you have to see this effect of magnitude of about 200 kilometers, which is quite amazing. In addition, it also see a flare around the galactic center at time frame of about July of 2018. Okay. What's interesting about this flare is that the flare, of course, is associated with the galactic center black hole itself. There's some gas around the galactic center black hole, and because of the relative astrometry, very accurately, they can track to micro arc second the motion of pieces of gas. Okay, and they see a motion roughly like this in a circular pattern. They assume this is an orbit at a speed of 3/10 of the speed of light at the event horizon, okay? So this is tracking a flare of some gas that's floating around the black hole, as we understand it, with a speed of almost 3/10 of the speed of light. So for this type of research, again, we can participate thinking about the next generation for this kind of inner stable orbit, last orbital point to see the gas in action. We can participate in the next generation of optical telescopes that I told you about, and I think we can continue. So now come to the one that I want to talk about, which is actually directly seeing the black hole itself, right? In the two previous experiments, one, you see some wiggles. Hard to explain to your neighbor on an airplane, right? If you say, I detected gravitational wave, they say, what does it look like? And you say, a bunch of wiggles. That's the end of the discussion. And then you can say the orbit around the galactic center, and you'll say, what does it look like? And you have these dots. That'll be the end of the discussion, right? But here, seeing is believing. I show you the picture of a black hole, right? So this is what makes it so important. So we are targeting supermassive black hole. Why? Because of the gravity, okay? The nearest two examples, the galactic center M87, has a shadow size about 40 micro arc seconds. So this, mind you, is the relative accuracy astrometry for the gravity experiment. But that size scale, we need to be able to image it. Okay, so images, we need the very long baseline interferometer, another elegant name, and submillimeter wavelengths. So what is the problem? The problem, of course, is that the size is actually quite small, right? Because the black hole is very small. For the ordinary black hole, no chance. Okay, but for these two cases, even though M87 is more than 1,000 times further away, it turns out to be roughly the same size as the galactic center at that size scale. 50 micro arc second, we need the size of a telescope, roughly the size of the Earth. If you work at 1 millimeter with a size scale of about 10,000 kilometers, you will get to a resolution of 20 micro arc seconds. So this experiment says, in order to resolve an image, to make a picture, you need to make d as big as possible and lambda as small as possible. Okay? What is the target of this kind of experiment? Direct proof of that supermassive black hole actually exists by seeing it. Imaging the shadow itself is to measure the metric, in the sense that the size is the mass, and then the spin is the shape. Okay? And then, of course, most importantly, test for general relativity in the case where the gravity is extremely strong. And the astrophysics, of course, there's still astrophysics involved relative to the supermassive black hole, namely how the stuff fall onto it and how the stuff come out of it. Okay? So this is the current, before this experiment, the best picture that we had of the galactic center black hole was 1/10 of an arc second. And then if you go 10 to the 5 times better, we are looking for this, right? Gas swirling in towards the central black hole. That's what our target is. Now, to back up a little bit, why are we interested in supermassive black hole? That is because for a long time now, we've seen that in galaxies, some galaxies, very powerful jets are coming out. Okay? The galaxy here is in the middle, in this little red dot. But very high relativistic jets are ejected on the scale of 200 megaparsec. You know, a galaxy, maybe 100 kiloparsec, right? So this is many, many times bigger. Jet comes out and then goes into a working surface where the stuff slows down and shock. Okay? The central black hole is ejecting extremely powerful jet, extremely high energy being this phenomenon. Where are these things? Well, if you look at the center of our galaxy, in the radial, it's actually quite messy. Okay, this is on the order of half a degree, or about 75 parsec. You'll see that there are things like this, which is an image of a supernova. There are some very intricate magnetic field threads. And then the galactic center is inside this splashy stuff. Okay, if you go to higher frequency, you can see that there's some splashy stuff here with filaments. This splashy stuff is most likely a supernova event. And if you go in closer, you'll find that there's some spiral-like material falling in toward a central dot right here. This dot, this is 8 arc second now, and this little point is the thing that we think is a supermassive black hole. Okay? So the point is to how to image that. The imaging, we thought we will make use of the SMA, which Taiwan is a party of, and to make use of ALMA, which Taiwan is a party of, and to take one of these telescopes and put it in Greenland in order to form an interferometer in order to resolve this object. Okay, that's our experiment. So what does it look like? What do you expect? So here are possible pictures of a supermassive black hole shadow. First of all, you get the shadow in front around a glow of material that's falling in. And depending on whether it's rotating or not rotating, you might see a little squashing of that image. And then depending on the flow, whether it's optically thick or geometrically thin, you may see the disk and you may see the motion of one side versus the other. Okay? And then the other case is M87. So this is the one that's, truly is a fantastic thing, okay? Because here's the optical picture. Okay? If you took an optical picture, you actually see the jet coming out, which is quite impressive, If you're an optical astronomer, you saw a picture of a galaxy, and you saw something like that, you'll be just truly astounded. There's some stuff spitting out in such a glow in the optical light. In the radio light, actually, you can see that, it is in fact, just like the other case, a very classical case of a jet with a lobe on the outside, which when you blow up, you will continually see a jet coming in, blow up again, continue to come in. Now you can get down to 10 milliarc seconds, still a jet is coming here. And then this is what the artists think. The jet is coming in right down to the black hole. Okay? Now, here it is. Here's what we had known about M87 for some time, namely from the stellar orbit. This is from the Hubble telescope. You can actually see the stellar motion around the center. And from that, you deduce that there's a mass on the order of 3 or 6 times 10 to the 9 at a distance of about 16 megaparsec. Okay? So that gives you a swashial radius of about 2 or 4 micro arc seconds. Okay? The VLBA at the same time measured this jet. This one, another very clever name, very long baseline array. It sees the jet and it sees the coming in, okay, of this jet towards the center. And people here sitting in the room, this is Keiji Asada and Nakamura-san, have been working on this for some time now, tracing back the structure of the jet. I won't have time to tell you all the details, but what I'd like to tell you is that in a series of experiments and increasingly high frequency, they can track the jet radius closer and closer to the center. The jet radius, turns out, has a parabolic shape rather than a conical shape. So there's actually a change in shape between the inner part and the outer part. But this inner part continues to go in, and it looks like it will land inside the event horizon or in shadow of the event horizon. So this is very interesting for us because we are looking to see what will happen when the jet comes in. Okay, and then one of our postdoc students from Taiwan, now a professor at Sun Yat-sen University, did a polarization measurement, and from this polarization measurement, they were able to deduce what the accretion rate has to be. And the accretion rate turns out to be very low. It's on the order of maybe 100th time that of the Bondi accretion rate. So significantly less than what you might expect for the accretion process, okay? So this is the picture. Here's the black hole. Here's the jet, the accretion flow on the outside. This is the innermost effective radius. And that's what we're trying to image to process in here. So here's some modeling of what it might look like. Here's the black hole in the middle, and then there's a jet on the outside, and here's various resolution and various picture that you might be able to see. This calculation in 2009 suggested that once we have ALMA, the image will begin to sharpen, and we'll add to that by adding the GLT. So what would you expect? So these are the simulations that have been done, right? Supermassive black hole, but of course you don't have a perfect telescope, so we thought that if we imaged it with the VLBI technique at 345 gigahertz, this is the image that we might obtain, okay? You see a ring, and you see the dispersion in the middle. Pretty close to what we actually saw, right? So if you have a jet, it gets a little bit more complicated because there's the accretion flow, but we also see the jet. So what will we see? So we calculate the simulation, as to whether this GLT will play a role on the summit versus without it. So this says that, indeed, the increased resolution, once we get to the Greenland telescope onto the summit of Greenland, we will be able to improve the image. Okay, so what has happened so far? In 2017, this Event Horizon Telescope consisted of 8 telescopes. And I want to point out that Taiwan plays a strong role in 3 of them. In ALMA, because we are a partner, JCMT, because we operate that as the East Asian Observatory, and then we also operate together with Smithsonian the submillimeter array. So we have 3 out of the 8 facilities. And here's the experiment on April 2017, various groups participating at the various sites. And here is a simulation of what happens when you do aperture synthesis, okay? The aperture synthesis is building up the coverage in the UV plane, okay? So you can think of this as a mirror, and we're just sampling more and more points of this mirror. As the Earth rotates, each of these tracks get longer, and as new stations come into view, they add new positions on the aperture, and building up this UV coverage, this is the UV plane, then you see the image continually improving as you add more and more baseline, right? This is the interferometer stuff that we all know. The second thing is the ray effect by having the ALMA telescope. So the interferometer works as multiplying the signal from a pair of 2 telescopes. So that if one of the telescopes have a very strong signal, that product is enhanced, right? So that is the role of ALMA. As one of the pairs, it will enhance that baseline sensitivity. And because of that, you can use it to phase reference, that is to correct the signal, okay? So here you are, we show you on the left, before you reference, phase reference, and after phase referencing, you can see that most of the error pattern is put back. We correct for the errors and therefore achieve a much higher sensitivity, okay? And then you say, well, what does the picture look like? Well, on the left side is what the dirty map looked like. On the right side is what happens after we've done our magic. Surprising, no? You might say, unbelievable, right? But first take some radio astronomy, then work with me on making maps for a while. Then you will understand this all works very well, okay? This process, weighting the data properly, we clean the map, we phase reference, self-calibrate, amplitude, self-calibrate. What does this mean, okay? Well, this image, of course, shows you the defect when you have a mirror and you're missing many pieces, right? An interferometer is basically a very large mirror, the size of the Earth in this case, but we're only sampling 8 pieces of it, right? You can smash a mirror, retain 8 tiny little pieces, and tell me, how do you reconstruct the image back to the way it was, okay? So you say, cannot be done. It can be done. To prove it, they have a Nobel Prize for it. It's called aperture synthesis, Rowland-Hewish. Why is this possible? It's because with an interferometer, we know exactly what is missing, right? It's very accurately known. Those 8 mirrors are precisely positioned so that they were in their original configuration, right? Phase coherent to a fraction of the wavelength, spread across the Earth. So if we're operating at 1 millimeter, we have to be phase correct to 1/20th of that wavelength across the Earth. We do this with atomic clocks so that we know exactly where we're pointed, positioned, and timed, okay? Then the error pattern due to the missing information is a sampling function that is multiplied to your real signal, okay? But everybody has done Fourier transform. You understand that a product, I can Fourier transform and then divide out the Fourier transform of the missing information. That's the error pattern. So the error pattern is exactly known. Then if I can remove it, then I can get back the original information, provided that it's sampled enough, okay? So this correction is a well-known technique. The fact that it works depends on having enough sample. If you don't sample enough of your aperture, then you'll have a problem, okay? The phase referencing and amplitude referencing has to do with redundancy. The fact that each telescope is measured against several others has a redundancy in properties, right? So you can measure, bootstrap your way back to insist that each gain fluctuation, each gain phase fluctuation are consistent with the behavior at all the other telescopes. So by this technique, magically we obtain this image on the right, okay? Believe it now? Here's the team in Taiwan, in Korea. You can see our student, W.P. Low from NTU, and Shigokuyama, Eiichi Asada, and various other people working on this. So why do we have this, you say? It's because we actually have 4 teams doing this, right? Because even we ourselves don't trust ourselves. So we have 4 independent teams working with the data. After it's calibrated in 3 different ways, then each of the team proceed to make maps and various techniques, clean, maximum entropy, to restore the image as best as we could. And then at the end, not having seen each other, they show each other the results, and they find that, in fact, they have pretty much agreed in the general result. What is the general result? It's black, it looks like a hole. Okay? And then, of course, you have various models that you can fit to these pictures in order to check what is the interpretation. So the first thing to note is that the time stability, because we actually did this experiment over several days. So here's the picture that's made in 5th, 6th, and 10th. And you can see that in each of those days, the image is roughly the same, Large scale, slight difference. Small scale, if you look very closely, is actually quite stable. This is actually very important because the small scale implies the data that's from the longest baseline, the highest resolution. The fact that they are stable likely means that it's tracking the event horizon, the small scale structure right at the end as it goes in, okay? So this tells you that at higher frequency, higher resolution, we have good prospect to continue to probe the more important part, which is what happens near the horizon. The fluffy stuff on the outside is just stuff falling in. What does the image say? Okay, first of all, the size scale. The size scale fitted the ring so-called photon ring, has a size of about 42 microarc-second. Here's the sun's orbit. Here's Pluto. Here's where Voyager is. That's the size, okay? That's about 6 billion solar masses jammed into the area roughly the size of the solar orbit, right? It's black, looks like a hole. That's the main conclusion. What about the physical parameters? What does it tell us? Okay, it tells us many things, okay? First of all, the photon ring, as I mentioned, is 42 microarc-seconds. The Schwarzschild radius is related by gm over c squared. This is almost Newtonian, but it's not. This is the proper relation to calculate the Schwarzschild radius. The shadow size by general relativity, by calculating how much the ray of light is spent in proximity to a mass, calculates that the shadow size should be about 5 times the Schwarzschild radius, and that's what we see, okay? So the shadow itself gives you a size scale, this size scale, which implies that the Schwarzschild radius is this size, a fifth of that, and that implies the mass of 6.5 billion solar masses, which is consistent with what we see in the stellar motions, okay? So it is this referencing to other techniques that have guessed the mass that allow us to deduce that general relativity is correct at that level in predicting what the shadow size could be. The ring brightness itself is also important. You measure the flux of the entire ring, and then you can calculate what is the plasma condition that will give you this kind of brightness. And I cannot go into the details of this calculation. Read the papers, and you will find that it implies an electron density of about 10,000, a magnetic field about 3 Gauss, and most importantly, the accretion rate was about 10 to the minus 3 solar masses per year, which is about 10 to the minus 5, the Eddington limit, okay? The ring asymmetry is very important, okay? It's brighter on the bottom. It's not asymmetric in some random way. Half of it is brighter, half of it is darker. And this turns out, we believe, to be consistent with rotation with Doppler boosting. So if the disk is tipped in such a way that you can see the motion of the disk relative to you, the part that's coming towards you, because it's moving at almost relative speed, close to the speed of light, will be boosted by this Doppler boosting. And the part of the ring which is moving away from you will be dimmer because of Doppler dimming. That's why the light is divided in half. One half brighter, the other half dimmer. Okay? It doesn't have to be like that. It turns out that's what it is. Okay? The disk itself, when you work it out, it looks like it's tipped so that it's perpendicular to the relativistic jet that we see. We know where the relativistic jet is. And the spin of the black hole, when we look at that, tells us that it's pointed away from Earth. Okay? So that's quite a few information just to show you how this works. Here's the spin of the black hole pointed away from you, away from Earth. And here's the spin of the material falling in. Okay? Here's the black hole pointed away from you. In one case, the spin is this way. In this case, the spin is this way. However, in both cases, the material close to the black hole will be forced to spin in the same direction as the black hole, right? Why? Because it's very close to the event horizon. It feels the full gravity dragging it as it is rotating. So if the black hole is rotating, the material right near the horizon has no other thing to do but to follow, okay? So this tells us very accurately that it must be spinning according to the black hole away from us. And in such a case, the bottom half of this disk coming toward us is brighter. The top half going away from us becomes dimmer. The alternative, if the black hole is pointed toward us, then that spinning motion will imply that the brighter part is on top, okay? So this is how we tell that the spin of the black hole is pointed away from us, but aligned with the jet axis, okay? This is another look at that. Just to emphasize, the emission follows the black hole rotation. It has to follow the black hole rotation. This is the black hole rotation. This is the stuff that's immediately around it. No matter how the gas is accreting on the outside, this way or that way, by the time it gets in the middle, it has to follow. Okay? And then that spin axis pointing away from the Earth, even though it's aligned with the axis of the jet. Okay, so here it is, the simulation of this Doppler boosting. Okay, on the left here is, of course, just the accretion, and on the right, you can see actually what happens as this disk is inclined relatively, right? So when it is in phase on, it is more or less the same brightness, but it is tilted, one side becomes brighter than the other. Okay, that is the Doppler boosting that's calculated by this group. And I mentioned to you here that we play a strong role. Keiichi Asada led the proposal writing team. Led the proposal writing team for the proposal in 2016, executed in 2017. In the proposal, this was the prediction. In the end, this is the image, right? So we can say that we were not that far off in predicting what we will see, okay? And that is the role that Taiwan has played in this particular game. So what's going on in the future? In the future, the idea is to go to higher frequency. The higher frequency will give you a better resolution, a more sensitive instruments. We're building new receivers, more station, adding Greenland telescope and others. We'll measure polarization. We'll do the Milky Way black hole. And then we might also look at merging supermassive black holes. The reason is that with this resolution, which can see the event horizon, we're hoping that if there are merging black holes in distant systems, even though we don't resolve them, we may be able to pick them up as a binary. And this will, of course, tell us the statistics of the binary event, the merging event, and that in turn will predict potential gravitational wave event that may or may not be detectable with the LIGO systems and such. So Taiwan will have increasing impacts. So what is next? Okay, so event horizon in 2018, the experiment that was done right after the one that was shown shows you that the GLT was actually in the system, and you can see that it has many important baseline that's added to it. Okay. So this telescope leverages what we already have in Taiwan in terms of SMA, ALMA, and JCMT. That's very important. Greenland, ALMA, JCMT, SMA. In the end, when we get to highest frequency, these will be the telescopes, the only ones that will work. Why? Because these other ones are on too low a site and will not be able to see it because the sky is not good enough. But at the highest frequency, Taiwan will have these assets which will perform the best resolution experiment to come. Time scale, maybe 3 years. Okay, the Greenland Telescope Project. What is the Greenland Telescope Project? The goal of the Greenland Telescope Project is actually to recover what we have invested on ALMA. Okay? So in 2006, we proposed to GoGoWare to fund us for this ALMA project in North America. And we provided 5% of the budget of what North America produced. And we wanted to recover this investment because from North American point of view, when they talk to me, they will say, have you transferred the money yet? And I would say, to do what? And they'll say, just transfer the money. And I said, not until we know what we're doing in Taiwan, right? You know, we need to do something in Taiwan that represents what Taiwan is pushing, not what money we're sending, right? So in the end, what we wanted to do was to extract this prototype antenna because I knew that the ALMA is producing the real telescopes, 25 of them in North America, but the prototype was just sitting there. So I want to recover this prototype, redevelop it, and to deploy it in order to extend ALMA capabilities. Because ALMA has a maximum baseline of 15 kilometers, I want to extend it to the longest configuration in order to do this experiment, right? So that was to recover what we have invested. So in the end, this telescope was awarded to our team. That's another story, how this happened. And then we also recovered some of the cash that I insisted we should keep in order to develop this project. So at the end, all of the ALMA budget that was put out by NSC was recovered in total so that I achieved zero cash outflow for this project, okay? So all the money was spent in Taiwan for Taiwan's initiatives. So this is to leverage the ALMA collecting area, attain the highest angular resolution, imaging instead of fringe fitting, Fringe fitting is one baseline at a time. I want to make a picture. This project was finally approved in Taiwan in 2008. We began this project in 2009. Okay, so 10 years. What do? We had to first work to get this telescope awarded to us in 2011. During the next 3 years, we actually retrofitted for polar condition. Why is that? Because in the pole, the temperature goes down to -60 Celsius. At that temperature, normal steel will become brittle. So we had to remove all the vulnerable part and replace it with cold temperature steel, right? And there's many other parts that need to be retrofitted. And eventually it was assembled and prepared during 2016, first at Norfolk Naval Space. Near there, I had a warehouse where we did the pre-assembly. Then we put it onto this boat, a Navy boat that is assigned to NSF, and that left Norfolk in order to go to Greenland, to the Thule Air Force Base in 2016, okay? And then the plan was to reassemble first flight in 2017, 2018, which we did, and then to operate on Greenland, which we did not. We did not get to the summit immediately in the year after. And that has to do with funding. So here's the picture of how it looks like. Here it is in New Mexico. Okay, the telescope was just sitting there. I think it's one of these. I'm not sure now. So small. Yeah, my eyes cannot see which one it is. But anyway, from there we removed this telescope, disassembled. And then we went to Norfolk, okay? Norfolk is a naval air base. You can see the aircraft carrier, okay? And the Navy boat came here. We had to put the stuff on here. And then it was transported out to Greenland, and it goes to this Air Force base, okay? So there's various options of what to do once you get there. For example, in the summertime, we have to live in tents on the summit. There's a station there that's right there right now. It can be serviced with a little plane as well as a big plane. Here's a picture of the Thule Air Force Base from Google. And here's the runway. And the boat docks at the cargo ship undocks here. And then we have to truck it over to the Air Force Base. Okay, Air Force Base goes to one of the hangars. And then actually the telescope is placed on one of these pads, okay, one of the landing pads. What's a landing pad? That's where the B-52 bombers used to be parked, okay? B-52 bombers are not there now. But actually, amazingly, Google is very high resolution, you know? So you can actually see the base of the telescope on that day. And here's our little trailers here. So nothing is behind the curtain. You can just go look, you know, and there it is on Google. It's quite amazing. So here it is, the shipping out from Norfolk base. Actually, this is the transfer of the telescope onto the cargo ship here. And I think this was me standing there watching this. Why is that? Why was I standing there? Because it cost me $50,000 to move these little packages about 2 miles from a warehouse to this. I was so mad that it cost $50,000. I said, you know, I gotta see, what are you guys doing? Well, why is that? Actually, it's very interesting. Because of what has happened, the Air Force Base has Navy base has barriers in the front, so that a wide cargo just cannot come on the base. I have to rent a tugboat just to move these pieces onto this boat. Okay, so here it is, the boat arriving into Thule. Okay, and once arrived, you know, we have to assemble the whole thing through these summer times, you know, and thankfully there's equipment because it's an Air Force base. And in the hangar itself, working at very cold temperature, this is Bill Liu, our chief engineer from Zhongkeyuan, who is our antenna partner for all these years. And he assembled these segments together and put the panels on, okay? So this took a few months. And then eventually the next year, 2017, this panel was carried out from the warehouse and then lifted onto the telescope. In the meantime, we have manufactured these electronics boxes in Taiwan and shipped them out also and assembled onto the antenna. We have to make these because in cold conditions, this telescope used to be sitting in a desert with no snow. And now we have all the rain and snow that we are expecting. We had to enclose all the electronics, and this was done in Taiwan. Here it is assembled, fully assembled in August 2017. Here it is. We are testing the receiver first at the JCMT before we went out. It was a 3-cartridge receiver system covering 3 frequencies. We installed it at JCMT in order to test it. Fully functional. Then we ship to Thule, plug it in, and it works immediately. So this says something about having a facility to mount your instrument to test before you go to the site. Okay. So here it is in Thule in January 2017. You can see the Aurora, quite beautiful. October, and fully assembled now on site in Thule Air Force Base. So here it is in the end of December, Christmas Day. We actually saw the moon in a scan with our receiver. This is Satoki was out there. Satoki is in the room. And Kevin Coy is also here from Malaysia. The 2 of them were there to actually measure the moon. And then this is followed by optical pointing and a spectral line detection. And there's Shoko, there's Satoki, Kevin, and Keiji measuring the spectrum. This shows that the frequency is properly tuned for this experiment. And then this was followed on with the VLBI test. Now this is with more of our staff, including Mingtang sitting here. And then we observed, this was interesting. We joined the Event Horizon Telescope experiment in 2018, right? But one of the experiments was to measure pole to pole between our telescope and the South Pole telescope. We were at 9-degree elevation, scraping the ground, and the South Pole was 6 degrees at the elevation, scraping the ground, to look at a source that's just between us. And that's the longest baseline VLBI ever successfully done. Okay, it was quite exciting that day. Okay, timeline. In 2009, we recruited these guys. Makoto Inouye, who was just retiring from NAOJ, and he brought his postdoc, Keiji Asada, to begin the VLBI program in 2009. Had they not come, this program could not get started. And then we were awarded the telescope in 2011, tested the site to verify the site is good on the summit of Greenland, retrofitted the telescope, tested assembly at the naval base, shipped to Thule by the Navy boat, assembled at the Air Force Base, tested the receivers, and then first light the Air Force Base, and then first VLBI image fringe with the Event Horizon Telescope. Aim to get to the summit in 2021 to 2022. What do we need to do? Move to the summit. In order to do that, we need to establish a base. We need to get housing and power. We need to transport. We need to construct, and we need to have winter over operations. So this is coming. So where are we? Money. This will not be cheap, right? So in Taiwan, we are always worried about money because we are finite. Okay, so I've used all the ARMA budget and some of IAA budget to get to this point. To get to this next point is another $10 million or more. Okay, so what is the answer? Answer: help is coming from Denmark. So knowing that we are going to Greenland, I have been visiting Denmark for the last 5 years. The idea is to get them to join. Okay, so they have a team already operating on Greenland. They are doing ice work. They do ice core drilling. So they have equipment, they have people, and we would like to collaborate with the Greenlanders also. But Greenlanders there are not that many of them. There's only 50,000 Greenlanders in all of Greenland. And Greenland is huge, okay? So they're all spread out in villages. So finding them to collaborate will not be easy. But we have a student who's been working with us. We hope to find more. But the key is the Danes, okay? So Danes, Greenland used to be their colony, and it is now a self-ruling property, self-ruling region. But Denmark still continue to pump a lot of resources there, and they are doing science there. What I told them is, we are in your backyard. If you don't join, it will be a true pity. So after thinking about it for 5 years, they now think they are interested. Okay? So they have sent me a letter of intent saying that they will join. So for that, of course, they will do the science. They will also deploy and commission with us. They will do the engineering up top, work on the construction and hardware. They will look for funding. They will look for funding for their postdocs and students and interns to join us, and then they will look for the budget for operation and so on. So, and most importantly, the politics and the interface with Denmark and Greenland, we need their help. Why is that? Well, actually, Greenland used to be very quiet, but at some point, Greenland was discovered to have quite a large rare earth elements deposit. Okay, although China controls 95% of rare earth elements, they've decided they need to control Greenland also. So they are interested. So the moment they're interested, Greenlanders start to think, we need to tax. We need to tax everything. So we are a little worried about what that means to us now. So the idea is that we need Greenland and Denmark to work with us. And then from there, we hope that we'll develop the first Arctic observatory. Generating energy will be an important problem. And then platform, once there, to have future experiments will be very good. And future observatories is something that we're planning on. So remind you, this is the first Arctic observatory, first major observatory in the pole in the north. There is an NSF station that's doing small science, ice core drilling, a little bit of atmospheric work, but no astronomical observatories in the north. The South Pole is full of telescopes, but the northern sky is left alone. So here's a project, first major project to be led by Taiwan. So I hope Taiwan will take a strong position. That's what we're working on. Okay. So summary, all of these research that we're talking about requires angular resolution, right? So gravity wave research is looking at the process of making bigger holes, bigger large, bigger black holes by merging, right? So the optical interferometry is working on the dynamics at the event horizon, and we are working on the actual physical processes at the event horizon and to test the GL effects in the future. So next generation, we're working on, we'll have more resolution, more sensitivity in all these domains, and we hope to make progress in this kind of science. So these are my final remarks on my last slide here. Why is this image so important? Well, the image makes what we imagined, what we expected from theory to become a reality. Okay? That's very important. As in Nobel Prizes are rarely given for theories. Why is that? Because theories are just theories. Okay? They're not real, right? The only thing real is observables. So when we see them, now we can say, okay, you guys were right. Okay? But don't expect a Nobel Prize. The image is very important because in the end, the data proves, right, that the expectations are real, right? This black hole existence has been debated for a long time. We know that it's there, but we've never seen it. Why does this resonate with the public? It's because for years and years, we knew this thing is not seeable, but now we can see it for the first time. The public naturally will resonate with that, right? Not a bunch of wiggles telling you that we detected gravitational waves, not a bunch of dots to tell you that we are moving around the event horizon. We are saying, here it is, it's black and it's a hole, okay? Measure the black hole properties directly for the first time. We will test general relativity. So I haven't given you a lot of details, right? But intuitively, this is right because we are talking about testing general relativity at the event horizon of a very massive object where gravity is overwhelming. Is general relativity still true? Looks like yes. But, it is still only testing at a factor of a few. We need much more detailed tests that will come. What is the problem? The problem, Taiwan, is how to compete internationally and get credit, okay? So all of you in the room, the young scientists, know this coming up, okay? How will we compete in the world? How will we ever get our fair share of credit? It's not simple, it's not easy. People are not just gonna hand it to you. You have to fight for that every step of the way, okay? How do you do that? You need to dominate. And to do that, Taiwan itself needs to support, okay? We need to generate that support for this kind of fundamental science where we'll actually make fundamental contribution. This is what we're telling our young people from Taiwan. You can work at the frontier and do very fundamental work, and you will get credit for it. At the moment, we are partner on 4 of the 9 EHD facilities. The plan for the future is to lead at the highest frequency and the highest resolution. I'll stop there.
Thank you, Paul, for the very wonderful, very exciting, very inspiring talk. So now we open for questions. Students, faculties. Yes, question?
Yes, Professor. Yeah.
I have 2 questions, Paul.
Yes.
The first one is that you were able to conclude on the radius of event horizon. Is there any way for you to infer on the mass radius? The second question is that do you see any hope that this project can earn you a Nobel Prize? If yes, then I think that the support within Taiwan would be enormous.
So the first question, do we see the mass, measure the mass radius? So as I say, the shadow itself, which I think is clearly what it is that we're seeing, okay? Why is it a shadow? It's because of the ring of light around it. Okay? Had we not seen the ring of light, I could not tell you it's black, right? It's black on black. It means nothing, right? Could mean nothing. But the ring, the fact that it's a ring suggests that, there is this depression in the light in the middle that's missing. And that size scale is scaling exactly with what general relativity says, which is that it should be 5 times the Schwarzschild radii. Okay, so assuming that general relativity is correct, 5 times the Schwarzschild radii gives me immediately the radii of the Schwarzschild radius, and from that I deduce the mass. 6.5 billion solar masses. That's the number. Oh. The mass radius. The radius is about 100 AU. Yeah, that's the size we measure.
Mass radius of this triple matrix.
So that's how much mass inside that radius. The distribution inside, I cannot tell you, right? That information is not available to us.
Well, okay, so let's
The second
see.
question.
Oh, yeah, that's yeah, I forgot. Sorry.
We never do science for the purpose of getting Nobel Prize. And we know that Nobel Prize is a very political process, right? And the problem with these things are not only political, but it's also about how do you gain recognition and credit. It's enormously difficult, okay? So never mind Nobel Prize. Control the direction of the project and how it's organized is quite difficult. Okay? There are 13 board seats on the Event Horizon board. Taiwan has 2 seats, myself and Makoto Inoue, representing our 2 facilities. One is East Asian Observatory, and one is the Greenland Telescope. From there, we push for the future of this project. Recognition comes always with a fight. Okay, for example, in Asia, we try to bring all the Asian astronomers who are interested in black hole science, in this topic, into the Event Horizon team. So we propose the membership. Okay, guess what they say when we do that? My colleagues in Europe and US says, we don't know that these people should belong to our team. We don't know them. Okay? We don't know who they are. My answer, if you don't know them, I don't know your people. Okay? What is the answer? They admit their members, we admit our members. Okay? It's a very uncomfortable situation to have to fight for your rights and to fight for your representation. News release come out, okay? News release comes out. There will be a quote from North America. There will be a quote from Europe. And I would say, where's the quote from Asia?
Well, my question is different from what you just answered me. I think that you have gained tremendous recognitions because the news appear in all, let's say, headline news in all the major international newspapers. What I'm driving at is that whether in your project you might be able to find something which will be significant enough to win an award?
That is an extremely difficult question.
Okay, so we can leave that
Yeah.
for some detailed discussion. I think we will get away from that.
I'll accept one from you.
Yeah. So one of the days, some of us sitting on the Nobel committee, then come back to tell us what's going on. Okay, so other questions? Yes.
Thank you for your really amazing talk. And so my question is, like you mentioned, that several different teams, like Clean RML, they use different algorithms and imaging processes to make different images, and they were compared. But how is it determined which one is more correct, or why is that certain picture image chosen to be the one to be shown to the public?
So
Thank you.
the first thing we feared was that the 4 team will come up with 4 different pictures that would make it, none of them would be reliable, okay? So the 4 pictures, once they are shown together, then what you do is you should difference them to see what the differences are and whether you think the differences are significant, okay? So there's a lot of vetting on the reality of the features, which are quite difficult, because each of those methods are significantly different, although the basic principles behind the data is quite similar, okay? But it uses different effects, okay? For example, cleaning is just using the error function and removing it from your map, okay? But it's a model-dependent thing, because in order to clean, actually we have to tell the algorithm where to clean. So there's a bias built in, okay? Because you have to sort of think, where do you think the source is? That's a difficult question if you start with knowing nothing. But we have a preconceived idea of, if the source is real, what size scale it should be, about what region it ought to be. And if you make interferometer maps, you will recognize the error pattern of the interferometer so that you can regulate. You can just, the experts will take a look at that and you'll say, these are the error patterns and this is the real source. Okay, we can discuss that. And then the other method is maximum entropy method, which is used in order to exercise the maximum likelihood of your solution based on various criteria. Sometimes a criteria might be, real features must be positive in signal. Negative things are not real. Therefore, you do not allow that in your model, right? So there's various techniques to optimize what your model ought to be. But each of them are different. So in the end, you want to compare them, okay? So it's quite controversial. That's why it took us a year before all the team finally agreed that what we see is reasonable.
But which one decided to be on the cover of some magazine or in the paper? That particular picture, how do you choose that?
Yeah, so it's the result that I think it's a weighted average of all the answers. Or what is it? Average, right? Average of the 4 techniques, right? 3 techniques.
Yeah. Well, okay. So other questions?
This project needs phase transition. The other parameter is money. Right?
Well,
So you can define the money from enterprise or Mr. Yang, Yang Xinlan.
well, so indeed, you know, big science requires big budget, right? And how much should a country,
台积电啊，或者鸿海啊，
yes, well, I am talking to them.
郭台铭这样选总统啊，可以。
Oh, okay, so let's come back to science. Okay. Yes, yeah.
So, what kind of is there any explicit test of general relativity that this experiment is considering?
So there are various general relativity models that's being built. I think if you read the papers, you will see that there are hundreds of images that were generated. Each model will generate various possible models. And I think the quote is that 90% of the models will fit. And the reason is that we don't have that much resolution at the moment. So the data, the image is quite fuzzy. So the detailed differences from the different theories are in the high resolution images that I showed before they were combined with the instrument. So only when the resolution is significantly improved will we be able to test some of these models. Okay. So.
Okay, so one more question. Okay, so I see one in the back. Today we have a lot of challenging questions.
As I know, the atmospheric condition in Greenland is not as stable as in Atacama. In particular, there is ice cloud if you observe from Greenland. So do you have any particular plan to deal with such issues?
So we did the survey. We had a radiometer up top to measure the sky conditions and then we collect the data as a function of time over a year, 2 year, 3 year, 4 year period to see what the opacity and stability look like from this radiometer. And what is interesting of that site versus, say, Hawaii or Atacama is that when the good condition comes, it actually lasts longer. Okay? So that has to do with the weather pattern. So when it's clear, it stays clear for days at a time, where other sites might be good for a day and then it goes bad. So each site will be variable. So in such global VLBI experiment, we usually schedule over a 10-day period. And every day we are standing by to check the conditions at every site. When all the conditions are good, we take data. Okay? And we typically schedule that over a period of 10 days. So you optimize for the 10 days of the year where most of the sites, all the sites are most likely to be good, and then you try for that experiment. So it's not a pre-known that it will work. So it requires a lot, okay? So just instability of atmosphere is also a problem, but in interferometry, this is one of the parameters that we fit for. So, it's another parameter in fitting of the data that we try to take that out, because typically, depending on the cell size, it will be the cell size of the atmosphere, it will sit on one telescope, right? So that effect on that telescope will be distributed, will be similar in every pair that has that telescope involved. So you fit for that parameter by redundancy with the other telescopes.
Yeah, I think I can add to Shina's question about the Nobel nomination. I think every once a certain years, some of the professors in Taiwan receive Nobel nomination, right? So many of the colleagues have received such a thing. So next time, you know what to nominate. Well, let's thank Paul for this wonderful talk. Thank you, Paul. If you still have some questions,